I'm just going to take a minute here and I'm going to go through the two in-class problems that we tackled on what we call the method of initial rates. So again, if you're asked to determine a rate law is a rate equals the rate constant times the concentration of A raised to the n power times the concentration of B raised to the n power. The only way you can figure out the three pieces of information that you need here are from experimental data. You can get rate information by looking at sample data like we had from kind of our first in-class problem, something that gives you a reaction rate, looking at a change in concentration as a function of time. So you can get this rate data in a lot of different ways, okay, but you have to get it experimentally, plotting the change in the concentration of one of your reactants as a function of time. Again, we're going to talk about here how you figure out reaction orders. So this is what our M and our N are. And how you do this is you compare rates of reactions as you change concentration. So with this first problem here, we'll see that there's different experiments that we have. We're looking at initial rate. So again, this is a whole bunch of data that we have here that's going to give us rates of reaction. And then we'll perform different experiments where we change the concentrations of both reactants. So we'll use that data to determine reaction order. And then in a later problem, we'll talk about how you get the last piece of information, which is actually your rate constant. So once you know certain rates, and you know from comparing different rate data what your M and your N values are, your orders, now you have just one unknown in your rate law, and that's your rate constant, so that you can solve for that. So we'll deal with a sample problem a little bit later that actually solves that. The focus of these in-class problems that we're going to work on, and then the sample problem that will follow, is actually calculating reaction orders. Okay, so the first problem that we have here is just a hypothetical reaction. A plus 2B goes to C plus D, and then we'll do a real problem, which has to do with reaction of O2 with NO. Okay, so what you need to do to figure out reaction order is you have to find two reactions that you're going to compare that keep one reactant the same and allow the other reactant to change. So for example, if we compare reaction 1 versus 2, and the lecture notes go into a lot more detail about actually what these values are. Since these values are pretty simple to do mathematically in our head, we're actually going to do that. If you need some more detail, go back and look at the lecture notes for the details of the calculations. But let's just kind of walk through this in our head. And what we're saying in comparing 1 versus 2 is we have to say what's the ratio of the rate change and compare that to the ratio of the concentration change. And what's really important again in choosing 1 and 2 to compare is we're holding one thing constant. We're only changing one variable at a time. And so what we're going to see is we're going to see the change in rate as we change the concentration only of A when we compare 1 and 2. So this is going to give us, so that gives us the order with respect to A. Okay, so let's look at the ratio of the rate change. Okay, so we look at the ratio of the rate change going from 1.75 to 3.5 times 10 to the minus 3 molar per second. We see a 2x increase in rate. And that's accompanied by, and again, this math with these values is pretty simple to just kind of look at. We see a 2x increase in concentration. So when we compare the rate ratio to the concentration ratio, we see that it's 1 to 1. And so that means that it's first order. So again, if we need to figure out with respect to B, so what do we want to compare to figure out the order with respect to B? That means we have to find two reactions to compare where we're holding A constant and then we're going to change B. So what we can see here is we can change the concentration of A here if we compare 1 and 3. So comparing 1 and 3 here, we can see that we're going to keep the concentration of A the same, but we're going to double the concentration of B. So again, the ratio of the concentration change is a 2x increase in concentration, right? if we're comparing 1 versus 3. So holding the concentration of A the same will allow us to figure out what the reaction order is with respect to the one that we are changing. So we can see that we're doubling the concentration of B. And if we come over here and look at our experimental rate data, we can see that the rate is also doubling. So the ratio of the rate change is also a 2x increase in rate. So this is also first order. So if we were to write the rate law for this, we could write rate equals the rate constant times the concentration of A, and it's to the first power, so I'm not going to write that, times the concentration of B, again to the first power, we don't write 1 there. And so it's first order with respect to A, first order with respect to B, second order overall. And again, this hypothetical reaction highlights the point that reaction coefficients do not necessarily imply reaction orders. Okay, so let's move on then and apply this to a real reaction. So here we have O2 reacting with NO gas to make 2NO2. So again, we need to find rates to compare that allow us to change one concentration while keeping one the same. So if we wanted to figure out, let's figure out what is the order with respect to O2. So to figure out what the order is with respect to O2, we have to find two reactions to compare where we're keeping the NO concentration the same, but we're changing the O2 concentration. So again, the order with respect to O2, we could compare 1 and 2, right? Because we're holding NO constant and we're changing O2. Now again, even though this is experimental data, we can look at the math and see that it's pretty straightforward here. Okay, it's not going to be the exact perfect whole numbers that we had with our hypothetical data, but it's still pretty straightforward. All right, so we're going to compare 1 versus 2. Okay, so again, we're keeping the NO concentration the same because we want to see what's the effect on the rate if we change the concentration of O2. So the ratio of the concentration change is 2x. We can see that. And then the ratio of the rate change. Again, it's not going to be a perfect whole number. If we actually work out the math here, we're going to see that it's 1.99. But that's close enough that we can round that up to 2. So again, a 2 to 2 ratio tells us that this is first order with respect to O2. All right, now again we have to look at what is the order with respect to NO. So we need to find two reactions to compare where we hold the concentration of O2 constant and then we change the concentration of NO. And while you can choose different ones, I'm going to choose 1 versus 3. You could choose other ones as long as we are choosing reactions where the O2 concentration is held constant. So you could choose 3 and 5 if you wanted, for example, and then you could look at the change in NO concentration there. I'm going to choose 1 and 3. So again, if we look at the ratio of the concentration change, so comparing 1 to 3, we're holding O2 constant, and if we look at the change in the NO concentration, we can see that it's a 2-fold increase. Then we need to compare that to the ratio of the rate change. So looking at the change in rate, and again mathematically it might not be obvious to see here, but this is 3.99. Now we can probably look at this and round it up and say that's close to 4. So if we doubled the concentration, we quadrupled the reaction rate, and that means that it's going to be second order overall. Now, part of the problem that we have here is 2 plus 2 is equal to 4. 2 times 2 is equal to 4, but 2 squared is equal to 4. So you got to remember that this is not a meaning that you'd double the concentration. It's actually a square relationship. And so if we double the concentration, then the rate is 2 squared. If we triple the concentration, then our reaction rate would actually be 9 times. That's a really important thing to point out here. So let's just kind of say that again. This is a square relationship, not a 2 times relationship. And so doubling the reaction concentration means we quadruple the rate. If we were to triple the reaction concentration, we would have a 9-fold increase in our reaction rate. So it's first order with respect to O2. Oops, I wrote overall here. Second order with respect to NO. And if we go ahead and write our rate law, so rate law, we write rate equals the rate constant times the concentration of O2 here. And again, it's to the first power, so we're going to not just write that there, times the concentration of NO squared. First order with respect to O2, second order with respect to NO, third order overall. So again, that's how you can figure out reaction order, is by comparing reaction rates to changes in concentration.